Hi everyone. In this video, I wanted to discuss a interesting topic. It is called injection locking, and this is in the context of oscillators and circuits. Okay, so in this video, we'll discuss mainly just the introduction, what it is, and the intuitive explanation of why it occurs from a circuit designer's perspective, at least. Okay, so let's get started. So what is injection locking, right? So what is this phenomenon of injection locking? Okay, so what it is that given, let's say I have some oscillator and it's oscillating at a free running frequency of F naught. And if I take another oscillator that is at F1, and then I inject this one's signal into F1 into F naught in one direction, right? So I have F1 and the signal goes into F naught, it doesn't go backwards. So let's call this oscillator 1, and I'll call this oscillator 0. Right, so if you have such a situation, then if the frequency difference between the two, F1 minus F naught, is bounded, so it's within some range, right? Then F naught spontaneously, guess that's the spelling, spontaneously oscillates. I should say, instead of F naught, I should say oscillator 0 spontaneously oscillates at F1 and has a well-defined phase relationship with oscillator 1. Okay, so F1 is oscillating, F naught is oscillating, oscillator 0 is oscillating at F naught. You inject at F1 some injected sinusoidal signal, and then spontaneously F naught shifts its frequency to F1 and starts oscillating at F1 as long as F1 is close to F naught. So that's the phenomena of oscillation, of injection locking. In circuits, at least, it's known as injection locking. In the general nonlinear dynamics kind of literature, this phenomena is also known as entrainment. So the name is different, but it's sort of the same phenomena. Okay. All right. So obviously the next question would be, okay, what if I'm beyond this frequency? What if I inject a signal that is not within this limit, right? It doesn't satisfy this condition. Okay, so let's ask that question and see what happens. Okay. What if F1 minus F naught is greater than delta F, right? Okay. Then you get this other phenomena related called as injection pulling. Maybe I should emphasize this better. Injection pulling, where oscillator 0 tries to lock. So it tries to make the right phase condition so that it is locked, but fails. Okay. And actually, if you look at it in frequency domain, the spectrum gets spread out, sort of. Or you could also think of it as getting corrupted. And we'll discuss sort of, this is just a phenomenological introduction. We will discuss injection pulling in a separate video in more detail as to what the spectrum looks like and quantitatively what exactly this is. But that's kind of what happens. So it kind of tries to lock, fails, and then the frequency kind of moves around. And even the phase becomes kind of unstable in some sense. Okay, so that's sort of an introduction as to what the phenomena is, but why do we care, right? So let's talk about that. So why is this important? Okay, so injection locking is actually very useful. So we will show actually that if you have one clean signal, let's say like a PLL, right? It can be easily duplicated, right? So you just make one PLL, one clean signal, and then it's at F1, and you have all these other oscillators that are, free running, so they're not well defined at F1. But if you lock F1 to them, they all start oscillating at F1. And we'll also show actually that the phase noise of a locked oscillator drops as long as the injected signal is much cleaner than the free running oscillator. Okay, so it actually leads to better phase noise performance and better frequency stability. Okay, assuming that your injected signal is clean in the first place, right? Okay. And then another huge advantage is quadrature signal generation. Okay, so what is that? In many receivers, you want to have IQ mixing, right? Or IQ mixer. So you want to generate from one oscillator two signals, one at 0 degrees and another at 90 degrees, right? So same frequency, but two signals that are offset by 90 degrees. It's very useful for IQ signal generation, things like that, and with receivers. And we'll show later that you can use that. What you can do is instead of injection locking, you can take two signals and then inject their oscillation signals using something called anti-phase coupling. And we'll see what exactly this is. And if you do this, then these two oscillators will now oscillate at the same frequency, but in phase quadrature. So strictly speaking, these two oscillators are not exactly, strictly speaking, this is not injection locking. It's like coupled oscillators because you're locking both ways, right? F0 and F1 to each other in a specific way called antiphase coupling. But we'll see that the phenomenon of injection locking will also explain this. Okay. And then there are other advantages. So other applications, I should say, subharmonic and superharmonic locking. So for example, you can actually lock from F0 over 2 to F0. So if you have a signal that's clean at F0 over 2, let's say at 10 gigahertz, and you have a free running oscillator around 20 gigahertz, you can create a clean signal at 20 gigahertz by locking it to a subharmonic. So it's like frequency up conversion. And you can do the same thing even the other way. So you want to make a frequency divider, then you can lock a 2F0 signal onto an F0 oscillator, and that will down convert your frequency by a factor of 2. Right? So that's another advantage. And there are many more actually. So I'll just briefly list them out here. You can do, so this is more on the research side of things. So where injection locking is being used today. There are some new ideas on using injection locking for large scale phased arrays, both at millimeter wave and for wireless power transfer. Right? So there are a lot of new ideas in this space. So this is still I would say it's kind of a hot topic now in some sense. So And then there's also some other papers that show that you can use these large scale coupled oscillators for uh, as Ising machines for NP hard computational problems. So I'm not going to go into this, but I'm just kind of giving you an idea. Uh, you can look this up. So people have shown that you can use sort of a second harmonic injection locked or coupled oscillators to solve what are known as NP-hard problems in computational combinatorial problems, I should say, not computational problems. Uh, and that's a very hot topic as well right now. So they're trying to kind of go beyond what a standard computer can compute, right? Okay, so enough about that. Let's look at the opposite side, which is the disadvantages, right? Or why another, I would say another reason to learn it. So let's just say five, right? Is you want to avoid injection pulling wherever you can. Pulling is generally considered to be bad, right? So if you have, let's say, some high frequency, not high power signal that you're transmitting from your transmitter, but you have a PLL nearby, right? And then there's some substrate coupling between these two. You can pull the PLL's signal with this high power transmitted signal, and you could have like two oscillators on the circuit or an oscillator and a clock signal that can pull each other and things like that. So understanding and quantifying, I guess, this phenomena of injection pulling as well will be very useful to us, especially when we do PLL design. So typically it's considered bad, but maybe if you like, you can try to think about how you can even use it, right? It's a phenomena. So, okay, so that's about the introduction. Let's move on to intuition. So this is the intuition from a circuit designer's perspective. And I'll leave a reference in the description for paper, I guess, where you can kind of get the basic ideas. Although I do uh, give a slightly different maybe description, but circuit design perspective. Okay, so let's start with discussing three different concepts. So the first concept number one, is let's say I have a RLC tank, resistor, capacitor. So I'm modeling a standard LC oscillator like this with some active element here, say a transistor, right? And then I take this out, and then I have an inverter back down here, and then connects down here. Okay, so I'll call this L, C, and R, and then let's label some values. So this is, let's say, IT. The voltage on this net is VG, and let's say this output voltage is V out. Okay. So obviously there's feedback here. You have an oscillator, you have a resonator, so you would expect this kind of circuit to oscillate, right? And we've discussed oscillators quite a bit already on the channel, so you can go back and watch those videos. We also discussed sort of a deeper look at LC oscillators with different models and things like that. But essentially, we'll use the simplest possible model to simplest possible analysis tool that we have, which is Barkhausen's criteria, I guess. And we discussed this a little bit in detail already, and I showed that, okay, Barkhausen is not necessarily very rigorous, but still very useful. And we'll see at the end of the video why it's not rigorous, but it actually does give us some really good insight, and it's very practical when you're studying oscillators. Okay. So what is that? So that says that if the loop gain is 1, so it's a very loose kind of description of Barkhausen's criteria. It's not necessarily exactly this, but let's just go with this. That if the loop gain is 1 around the loop, then this circuit oscillates. Okay. So that's what we'll go with. All right. So which means that, I start from some point, I go around this loop, right? And if the entire phase shift over the entire loop for the signal is 0 and the gain is 1, then this circuit, this loop will oscillate, right? Okay, again, I just want to point out that's not very rigorous, but still very useful. Okay, so let's actually do that. So we'll do this using phasors. So let's assume VG. Maybe I'll use red. Okay, so the phasor for VG is like this, right? It can be arbitrary in any direction, but I'm just setting it like that. Okay, then we know that VG and IT are in phase, right? Because when VG increases, IT going this way increases. So the way I've drawn IT is going down, so that increases, right? So which means that IT and VG are in phase, okay? All right, and IT and V out are out of phase, right? Because when this current IT increases, and let's assume, okay, we are at the oscillation frequency, which is F naught. So at the oscillation frequency, L and C kind of are resonating with each other, and the impedance of this tank is purely real, right? Which is R. We'll get to that maybe a little bit later, but if you know that already, then that's good. But if you don't know it, then just kind of take my word for it that when this kind of at the oscillation frequency, or at the resonance frequency, not the oscillation frequency, sorry, at the resonance frequency of this tank, the impedance is purely real, which is R, which means that V out. So let's write it out, right? So V out is, V out over IT. And the angle of this is 180 degrees, right? Because VDD minus V out over IT is purely real, and that's R, right? So if you look at it at an AC condition, then this VDD goes away, and then you get V out over IT is minus R, right? Or R is minus V out over IT. And that's why IT and V out are out of phase. Okay. So V out would be in this direction, right? And then when we go through this inverter, V out gets flipped again, and then we come back to VG, which means that we come back to VG, which is out here, right? So that essentially completes that loop gain criterion of loop gain being 1 and the phase over the whole loop being 0. And that's why they say that at the resonance frequency, this circuit will oscillate, because at the resonance frequency is where this Barkhausen criteria was satisfied, right? Because only at the resonance frequency, this condition is true. Okay. So that's why they say, okay, this circuit kind of oscillates at the resonance frequency. All right. So let's see what happens if we, let me actually just kind of finally mention that. Implies circuit oscillates at omega naught, which is the resonance frequency of the tank, right? And that's 1 over square root of LC. Okay. So let's introduce a second concept. Sept. So let's again redraw that circuit. So I'll actually just copy it. Okay. And now what I want to do is introduce a phase shift here. Call it V naught if you like. And then still have my transistor there and then ground. So now this is VG again. And then this is I oscillation. And this phase shift is in current, and we'll see how to do that. But this is your IT. Okay. So now again, if you go through this kind of Barkhausen criteria and see now what happens is that we start with again VG. So let's say that's VG. Then you have I oscillation in the same direction, right? Of course, because that's determined by the transistor. And VG and I oscillation for an ideal transistor are in phase, right? I oscillation is GM VGS, which is VG in this case, and GM doesn't have any phase term, right? Okay, and then we said, okay, there is some phase shift now. Sorry. Um, between I oscillation and IT, right? So that means IT has some phase shift, and this phase shift is the phi naught that we introduced there. Okay. So now at the resonance condition, sorry, at omega naught, which was 1 over square root of LC, V out would have been here, right? Okay, if V out was there, that's a problem because now when you go through the inverter, you don't come back to VG, right? So you actually want V out to be here, right? So if you want V out to be there, that means that V out and IT have to have a phase relationship now, right? So which is exactly equal to phi naught. Right, so if you actually plot the phase of the tank, so this is sort of the tank phase as a function of omega, right? So that looks something like this, right? And then at omega naught, this was 180 degrees, and that's only because of the way we've drawn the currents here. But what we really want is not 180. We want something that's less than 180, right? Because essentially you want the phase shift to be only this much. V out over IT to be only this much. Or you could say V out over IT is actually this large one. So it's maybe more than 180, right? Whichever way you look at it, you need to be offset from omega naught at some omega 1, right? So that the phase now is 180 minus V naught, let's say, right? So that's actually why the oscillation frequency now has to be at omega 1, right? So when you introduce a phase shift here, the tank now has to resonate at a slightly different frequency, omega 1, so that the loop gain condition of phase being 0 when you go around the loop is satisfied, right? And that's sort of the basic idea behind why injection locking shifts the frequency. Okay, but that's not exactly injection locking. This is not the final concept yet. So if you introduce a phase shift in an oscillator, the oscillation frequency shifts from the resonance condition of the tank to a slightly off resonance frequency so that the oscillator oscillates so that the phase condition is uh, is met, and that offset frequency is now where the phase condition is met. So the oscillator oscillates at the offset condition, right? Okay, so that's the second concept. And so far we haven't done any injection locking. This is still a concept in oscillators. So you can actually build an oscillator, introduce a phase shift, and you'll see that when you change this phase shift, the oscillation condition changes. Okay. Okay, so I should say that in this case, the loop gain condition is satisfied at omega 1, implies the oscillation occurs at omega 1. There is kind of a drawback to this kind of approach, but we'll discuss it at the end. I mean, if you want to know what it is, then you can kind of see that. Okay, I don't want to say anything. Okay, so let's just assume that this is true. So intuitively, at least, okay, now the loop gain is satisfied, the loop phase condition is satisfied at omega 1, so the oscillation occurs at omega 1. Okay, very nice. So let's go to third concept, which is injection locking. Right, so we want to see, okay, what if we do actually introduce a phase shift between the two sides. So I'll again make a copy of this. That. Oops. Then okay. So now what we want to do is we want to introduce a phase shift by injecting a sinusoidal signal, an injection into that node. So why does that introduce a phase shift? Just use KCL and you'll see that. So if I injection and I oscillation and are different, have different phases at a specific frequency, if they have different phases, then we see that I oscillation from KCL plus I injection should be equal to IT, right? So now you essentially introduce the phase shift here of phi naught. Okay, so let's go through this phasor diagram again and see what happens, right? So you have VG again. This is VG. You have I oscillation, right? And now I oscillation gets added with I injection. And you have IT coming out from that. And again, it's the same picture, right? IT is slightly phase shifted. So the tank now has to oscillate at a slightly offset frequency so that the out ends up here. And then when you go through an inverter, you're back to VG, right? So that the phase condition is met. Okay. So keep in mind that here we are kind of looking at this phasor diagram at omega injection. Okay. So phasors, of course, have to be at a single frequency. So we're looking at this entire phasor diagram at omega injection. So this doesn't really explain the mechanism behind or the dynamics behind how injection locking occurred. But what I'm saying is that after injection locking has occurred, if everything in this circuit is at omega injection, so this is at omega injection, this is at omega, all of them at the same frequency now, once it has gotten locked at omega injection. Okay, all of these are at omega injection. Then you can draw a phasor diagram. And the phasor diagram is such that I oscillation and I injection, when they add up, you get IT. That introduces a phase shift between I oscillation and IT. And that phase shift basically forces this tank to oscillate at a slightly to resonate forces the tank to be such that the phase shift here in the tank is equal to phi as well, so that you kind of undo this phase shift between I oscillation and IT, and you restore the phase condition, right? But one question that remains is that, okay, I injected at omega injection, but why does the tank have to satisfy the phase condition at omega injection, right? So we are saying that you injected a signal that had some phase shift with the oscillation signal. that introduced a phase shift between IT and I oscillation, but why does the tank have to oscillate at exactly omega injection so that it cancels that phase, right? And the reason that happens, which I'm not going to give you like uh, a very rigorous explanation here, but we'll do that in a future video. But the right way to think of this is like this, right? So this is sort of the mechanism. So let's actually write down the mechanism. The intuitive kind of approach to how this is happening. Okay, so the step one was omega injection is injected into the oscillator. Okay, so the oscillator was doing its own thing, oscillating at some omega naught, and then you injected omega injection into the oscillator. Okay, then at omega injection, right, the tank phase is offset by P naught, let's say. Okay, so originally the oscillator was oscillating at F naught, where the tank had no phase shift except for the 180 degrees. But now at omega injection, which is slightly offset, the tank introduces its own phase shift, phi naught, right? So then what happens is that the oscillator locks onto omega injection with a phase that cancels P naught to restore the loop phase condition at omega injection. So that's exactly the mechanism, right? So essentially, I should say that I oscillator adjusts its phase with respect to the injection to satisfy loop phase condition at omega injection. Okay. So if we summarize, essentially what happened is that, okay, you injected a signal at omega injection, and now the tank introduced some extra phase shift at omega injection. So the oscillator at omega injection produces the right phase shift between because the free running oscillator can set its own phase, right? It's free running. So it sets its phase in such a way that the Barkhausen criteria is satisfied around the loop. And that's the right way to kind of think about this, at least intuitively. Okay. So that's why it starts oscillating at omega injection, is that at omega injection, it can produce the right phase shift so that the Barkhausen criteria can now be satisfied at omega injection. Okay, so that's sort of the intuitive explanation of injection locking. And the big question now that you should have if you've been paying attention closely is that, okay, we said that well and good, at omega injection, now the Barkhausen criteria is satisfied around this loop. So it's oscillating at omega injection, well and good. But at omega naught, which was the free running frequency, this doesn't have any impact, right? So at omega naught, also the Barkhausen criteria should be satisfied. The loop phase condition should still be satisfied, right? But does it also oscillate at omega naught? No, it doesn't actually oscillate at omega naught. And this model or this intuitive picture, circuits picture doesn't exactly tell us why, right? Because according to Barkhausen, it should oscillate at both frequencies. But that's the reason why Barkhausen is not the right way to analyze oscillators, is because Barkhausen relies on linearity. And the fact that this condition is met at omega naught and omega injection comes from the fact that this entire circuit model right now is a linear model, right? Whereas you can't actually rigorously analyze oscillators using a linear model. And that's the reason why in future we look at a better nonlinear approach, maybe not better necessarily, but a nonlinear approach to analyzing injection locking, where we'll see that okay, this oscillation frequency shifts to omega injection. It's not like you have two different frequencies at the same time. But anyways, it still gives you a lot of insight to say that, you know, this guy introduces a separate phase shift, and now this oscillation with respect to this has to satisfy a specific phase requirement so that Barkhausen criteria is satisfied. Okay, so essentially there is a relationship between omega injection and I oscillation phase when locked. And we'll derive an analytical expression for that relationship based on exactly this model even. So that's why I'm saying this model is still kind of very useful, right? Even though it's not super rigorous, this relationship, especially between I injection and I oscillation, and also the tank's impedance, we'll use to derive this relationship. And this relationship, exactly the analytical relationship between these two quantities, the phase of the oscillator and the injection frequency, is given by Adler's equation. Adler's equation actually is a little bit more general than that, but you can derive the relationship from Adler's equation. As a special case is will give us this relationship. Okay, so to summarize, probably I'll stop here, and in the next video we'll derive Adler's equation based on what we've discussed here. And we'll do a very general derivation with just a few assumptions. Essentially, we'll just use this and tank impedance to derive Adler's equation. Okay, so that's injection locking. Hopefully that was somewhat clear. If you have any questions, please leave them in the comments, and look forward to the next video where I derive Adler's equation. Thank you.